Okay. You know that this is what our problem started with. We have two densities slightly overlapping, and then we want to make a good rule for classification. In the present example, f1x is normal with mean 0 and variance 1. In the second case, it is normal with mean 2, because you can see here it is 0, it is 1, it is 2, it is 3, it is 4, it is 5. So it's a mean at 2 and variance at 1. So f1x is normal 0, 1, f2x is normal 2, 1, and we want to make the rule of classification. By graph, we have pointed out that x equal to 1 is the line that makes the separation, because whenever x is less than 1, f1x is larger than f2x, and so point is supposed to lie on f1x side. If x is greater than 1, f2x is supposed to be larger than f1x, and point is supposed to lie on the second distribution. We want to derive this mathematically, and so our today's aim is to derive this mathematically. Okay. Now, while deriving this mathematically, we know that this is the rule we have: f1x 0 upon f2x 0 greater than or equal to 1. So we'll start with this. So let me write first of all f1x, let me write f2x, and then we'll start. f1 f1 x, what is it? It is 1 upon square root of 2 pi, 1 upon square root of 2 pi. Okay. Square root of 2 pi, then exponential of minus 0.5 and x square. This is what the f1x is. Now similarly, let us see what is f2x. Similarly, let us see what is f2x. So f2x is this one, right? Okay. Now our rule says f1x upon f2x greater than or equal to 1, f1x f1x upon f2x greater than or equal to 1 implies that an observation will belong to, will lies in first population. This is what the meaning is. And let us see what that rule comes to be. What this rule comes to be, let us see. Yes. Let us see what this rule comes to be. Now, if I put this f1x upon f2x, you will see that the constant 1 upon square root of 2 pi will get cancelled. If I write f1x upon f2x, means ratio of these two densities, obviously this 1 upon square root of 2 pi, 1 upon square root of 2 pi will cancel. And what I can write is this. This divided by this. Greater than or equal to 1. Greater than or equal to 1. If this condition is satisfied, we will say that the observation will belongs to first population. Now, if I change the side, I can write this equation as, or this inequality as, I can write like this, right? If I change the side of this denominator to this side, I will get this. Now, exponential is common. So I can write another way and see how I can write is this. I can write this way. I can write like this. And see now, see now, both have minus sign. Both have constant 0.5. So I can write this as now, using my mathematical knowledge, I can write this as, this inequality will change. This inequality will change and it will become less than or equal. And it will become less than or equal. And if I square this, if I square this, it will become plus, sorry, minus 4x plus 4. This is what the square of x minus 2 brackets square will come. And so at the end, what I get is this. At the end, what I get is this. I can cancel this x square. I can cancel this x square. I can write plus 4x to this side, and I can cancel this minus 4x. So the last thing what I get is x less than or equal to 1. X less than or equal to 1. And so what it means is whenever your x is less than or equal to 1, an observation will belongs to first population. So this is the rule, the simple rule. It's very simple rule. What it says is very important. That you are just going to observe the observation. That's all. You need not have to do any calculation. You need not have to do any calculation. Simple observation. What is the value of that observation? Less than or equal to 1. It will belong to first population. What is the value of observation? Greater than 1. It will belong to second population. And that is what we are observing here. So see, geometrically you can predict that x equal to 1 is the possible cutoff point, and mathematically also you have proved the same thing. Mathematically also you have proved that x equal to 1 is the possible cutoff point, right? Okay. This is one thing we have to explain. This is one thing we have to understand. Now we'll go to the something different case, and that case is very important to understand. What is that case? Assume that P1 equal to 0.7 and P2 equal to 0.3. So let us assume that these are the prior probabilities. Let us assume that these are the prior probabilities. And now we'll think first, before going to its mathematics, we will try to think first that what will be the possible case, what will be the possible situation. P1 equal to 0.7, P2 equal to 0.3. So let me again take this to this side. Okay. P1 equal to 0.7 means what? 70% chance that observation will belongs to first density. 30% chance is that the observation will belongs to second density. And so there is no equal chance. More chances are belonging to first density. It means what? If you have 10 observations for classification purpose, then out of that 10 observation, possibly 7 will belongs to first population and 3 will belongs to second population. Now in this case, where will be our cutoff point? That we have to understand. And once we understand this, its mathematical derivation is simple. Where it will be, whether it is to the left of x equal to 1 or to the right of x equal to 1. Yes, can anybody guess that cutoff point will belongs to left of x equal to 1 means to this side or to this side? You have given that prior probability of belonging to first density is 70% and prior probability of belonging to the second distribution is 30%. So anybody can have guess. See, more chances are there. That means your cutoff point should belong to greater than equal to one side, because you are giving more scope. Because you are giving more scope. 30% chance is it belongs to second density. So you have to give less scope for second distribution and more scope to first distribution. So let us try to derive this case also. Let us try to derive it. Now for this purpose, I will consider this rule. I will consider this rule. Yes, I will consider this rule. Because in earlier case, we have the cost of misclassification same, prior probabilities are same, but here cost of misclassification is same, but prior probabilities are different. And so my rule will be like this. My rule will become like this. Yes, this will be my rule. This will be my rule. F1 x0 upon F2 x0 greater than or equal to P2 upon P1. Okay, it is my rule. So let us see how it is. Let us see how it will be. So from this, I will take this one. Yes. But now, instead of 1, now it is something different. And what is it? It is 3 by 7. It is 0.3 upon 0.7, means it is 3 by 7. It is 3 by 7. Right? And so now we can write this as, it is very interesting. I can write this as 3 by 7 here, star here, and this greater than or equal to sign will appear to this side. Because just what I have made is the change of this denominator to the right side. That's all. I have made the change of this denominator to the right side. That's all. Now, if I take, in earlier case, this constant was not there. So exponential base same. So I made exponents to be same. But in this case, you can't do that. You have to take log on both sides. And so if I take the log on both sides, what I get is this. If I take log on both sides, means log to the base e, ln of e. Because of log rule, it will become plus, and we are here. So we have to take care of this plus minus sign. It will become minus only, and I can write like this. I can do this also. So what is the log of 3 by 7? Natural log of 3 by 7. So let me compute it. I will compute it and I put it there, 3 by 7. I will compute the log of 3 by 7, and we will write there. Okay, see, it comes to be minus 0.8473. And so I will write this as minus 0.8473. This is the log of 3 by 7. Okay, this is the case. And now you can say, now you can see all three have minus sign. And so we can rewrite this by changing the inequality. By changing the inequality, and we can write like this. But here I have to make a small change. It is less than or equal. Okay. Now this is a quadratic equation. See, this is the quadratic equation, and we have to solve this. So I will go to the next slide. I will take this to next slide, and we'll see how it comes to be. It is very interesting to solve and to get the answer. Okay. Now see here, if I am going to solve this inequality and square this, what I will get is, let me write this, take this as okay. This is 0.5. First of all, let me square this bracket here itself. X square minus 4x plus 4. This is what my square is. And again, what I will get is this 0.5 x square can be cancelled with this 0.5 x square. Or let me keep this as it is. Here I can write 0.5 x square minus this will become 2, and this will also become 2 because I am multiplying by 0.5, so it will become half. And now this 0.5 x square and this 0.5 x square will get cancelled. Okay, so let me cancel this. Okay, okay, 1 minute. Let me copy this and write it here. And now see what will happen is this minus 2x will become to this another side. This minus 2x will become to another side. I can cancel this now. Okay, minus 2x have already gone to this other side, and I have here now 2.84 like this. So if I divide by x, what I will get is, it is very interesting. If I divide by 2, I will get 1.423 and then 6. This is what I get it. This is what I get it. X less than or equal to 1.247x. It means what? Your x cutoff point will be to this side. 1.42 means it is nearly about close to 1.5, right? So this is the rule. This is the rule of classifying an observation to F1 or F2 if prior probability is 0.7 or prior probability is 0.2, sorry, 0.3. And so as your prior probability P1 increases, this cutoff point will be going close and close and close to 2. As your prior probability will decrease, this point will shift to the left side. The point is what I told you already, that at equality, when prior probabilities are equal, you are here. When prior probability P1 is larger, you are to this side. When prior probability is less, you are to this side. That is what the point we have to mention here. Now you can take an example. You can change your prior probabilities and you can see how the cutoff point X will change. So this is one example I want to discuss here. Now the second example that we will discuss is as follows. And for that, I will go to Desmos first. I will go to Desmos first because I want to, I cannot minimize my, okay, okay. I will go for Desmos. I will go to Desmos. Okay. Okay, let me share my Desmos. I have shared my Desmos here. Okay. And now what I will do is f of x equal to square root of 1 upon, 7 upon 44 7 upon 44 and exp exponential of minus 0.5 x square. This is what the normal density I will going to consider. And the second density what I am going to consider is, say, let us write this as f1x. Second density what I am going to consider is 7 upon 22, 7 upon 22, 1 upon 1 upon 1 plus in bracket x minus 2 bracket square. See this. Let me do some basic changes here. Just to okay. Okay. In fact, I can do this also. Right. So one is the normal density, another one is a uh, Cauchy density. And you can very well see that one has a mean, other one has no mean, but it has a center say at x equal to 2. It's a location parameter, you can say at x equal to 2. But variation is different. And so even though they are symmetric, they do not match. And therefore, you cannot think of this point as this point, say x equal to 1.2, you cannot think of this as a cutoff point. In this case, cutoff point will be something different. And so let us try to see how this cutoff point will be. So again, I have to come back and I have to share my different CD. Okay. So here, again, we will go with this. Let me take this as, okay. Our first density is okay. But second density is what? It is 7 by 2, and then it is 1 upon in bracket 1 plus in bracket x minus 2 square. So we have to make this. We have to make this. So f1x upon f2x greater than or equal to 1 implies observation will lie in the first distribution. We have to simplify this. And I will ask you to do this simplification and see how the cutoff point becomes. Correct? So you are supposed to do the further simplification and tell me tomorrow what is the cutoff point. Right? X equal to what? This we have to tell me tomorrow. Okay? So with this, we will stop for today.